So there are several things that you can do with any sort of a graph. Now in this particular case, most of you can see that it's a velocity time graph with velocity measured in meters per second east on the y-axis and time measured in seconds on the x-axis. So right off the bat, let's just start off with a quick review of, I guess, grade 9 and 10 math. If we want to find the slope of this line, most of you know that the slope of any line is basically nothing more than your rise over run, which in this case is nothing more than your change in what you have on the y-axis divided by what you have as your change in the x-axis. Okay, let's do a quick little calculation here. If I just work things all out, if I take a look at the y-axis, my change in y is really nothing more than a change in that particular variable, which in this case is the velocity. So we're going to write that down as v2 minus v1 divided by my change in what I have on the x-axis, which is of course time t2 minus t1, or just delta t. And if I take a look at the points I'm going to use to calculate this slope, it's often best to try and use the very first and the very last point as well. Reason being, this often gives you the most precise version of your calculation or of your calculated slope, so that's why we tend to choose those two, although most students tend to take the ones that are most convenient for you. But in this case, let's choose these two since they are convenient as well. So if I do the calculation itself, it looks like we have, let's just have a quick peek here, it looks like 36.0 meters per second as my value for V2 minus 0, divided by, in this particular case, 8.0 seconds minus 0 as well. So all I'm going to do now is do a final calculation. And if you work this all out, it turns out to be about 4.5 meters per second per second. Now, it's really important for you guys to note that if you take a look at those units, I think most of you might recall from last year that this actually works out to be 4.5 meters per second squared. Now, it is also a positive value. So if you take a look at the y-axis on the graph again, you might notice that the positive values in this case are represented by what I've labeled as east. So I'm going to do the same thing here. I'm going to say that since my answer 4.5 meters per second squared is a positive value, I will label this as east as well, and that's all you'd have to do to calculate the slope. Now, I think if you take a look at the units, you might notice that they work out to be meters per second, and you might say, well, how did I get from meters per second to meters per second squared? Well, if I take a look at the unit analysis, I think most of you can see that meters per second is the unit that I have on the numerator side, so I can actually write that down as a fraction, meters per second on the numerator side, divided by my seconds on the denominator side. So if you take a look at that seconds, it can actually be written as seconds over 1, and most of you know that whenever you have a fraction divided by a fraction, that's actually the same thing as writing this down as the fraction on the numerator side times, in this case, the reciprocal of the fraction, 1 over seconds, on the denominator side. And most of you can see that if I look at the numerators, you just get meters, and on the denominator side, you get seconds times seconds, which is seconds squared, and that's why we get meters per second square. Okay, and I think that pretty much sums it up. Now, one thing I want you to note that is that meters per second squared, from what you remember in grade 11, is of course your unit for acceleration. So naturally, if you take a look at the graph in itself, recognizing that it is in fact a velocity time graph, let me just write this down actually. If you have a VT graph and you find the slope of this VT graph, obviously that's going to give you information regarding acceleration. Okay, so hopefully that makes some sense. That's of course a review from last year's course. If you look a little bit further on this handout, you might notice that now what we're going to do is try to find the area underneath the graph. So what we're going to do is go back to the original graph again, and this is something that we did yesterday. So if I want to find the area under the graph, what we're basically doing is we're going to try to find the area underneath the line itself and the x-axis. So in this particular case, I just want to find the area of what I've just shaded in. And as you can see, it is, of course, a triangle. Like we said yesterday, what we're going to do is we're going to see if we can find the area of that particular shape. So in this case, area is equal to 1/2. Most people say base times height. Why not height times base? Good. So if you take a look, 1/2 is just a variable 1/2. The height of this particular graph, let's just take a quick peek here. It looks like I would say the height now in this case we have a position time graph, and as you can see, it's not a linear relationship. It actually shows two separate things, and most of you can recognize that if you take a look at the first, I would say the first 4 to 5 seconds of this particular object's motion, so from here to about there, we can all agree that for equal intervals of time, you can see that its displacement is increasing. So most of you can see that the object is, of course, speeding up there. And if you take a look at the second half of its motion, so from about 5 seconds to about 11 seconds, again, you can see that for equal intervals of time, we do have an increase in displacement as well, but that increase actually gets smaller and smaller and smaller over equal intervals of time as time increases. So we can say that from 5 to about 11 seconds, the object is, of course, slowing down. One thing you might recall learning to do last year was learning how to find the slope of the tangent line. So we're going to see if we can review that right now. So I'm going to just zoom in a little bit here. So let's just say we're interested in finding the slope of, let's rephrase that. Let's say we're interested in finding the instantaneous velocity of this particular object at, let's say, 3 seconds. So what we're going to do is we're going to see if we can locate 3 seconds. There we go. And in order for me to find out what the object's instantaneous velocity is at that point, we need to draw a tangent line. And then once we draw that tangent line, we're going to see if we can find its slope. Now, how do you draw a tangent line? Well, what I'm going to do here is see if I can draw a straight line that can actually run parallel to that particular point of the graph so that it only meets that point once. Now, this takes a little bit of practice, but what I'm going to do is see if I can get a ruler here. Okay, so here we go. So here's my here's my makeshift line. So what I'm going to do is I'm going to see if I can put this tangent line right up against the 3-second point on the graph. Now, most of you can see that it's actually not quite parallel to that point. So what I'm going to do is try to maybe angle this off a little bit. Come on. Okay, and I think I pretty much have it, so I'm going to see if I can. That's good enough. Yeah, that's fine. Okay, so if you take a look at this line that I drew, you can see that that it is in fact a tangent line. What I mean by that is that if I were to zoom in and zoom right into that point, you'll see that at what did I do that for? You'll see that at exactly 3.0 seconds, my tangent line is exactly parallel with the line on the graph, and it only meets that point once. Now, if it runs exactly parallel, what I'm basically doing is I'm finding the slope at exactly that point. And to do this, we're going to zoom out again, and this is a little tricky there. And what I'm going to do is see if I can find the slope of this tangent line. So once again, like we did before, the slope of any line is going to be rise over run. Now in this case, it's a position time graph, not a velocity time graph. So I'm going to find my change in position, which in this case can be written as d2, my final position, minus d1, my initial position, divided by my change in time. Okay, if I take a look at this particular graph, let's do a little estimation here. My final position is my position at this particular point, and it looks to be about, I would say about 96.0 meters, so 96.0 meters, minus d1, which is that point over there, and I'm going to say that's just 0. And all of that divided by my change in time, so my t2 minus t1, t2 looks like, I don't know, what's that, 9.5 seconds. So let's write that down, 9.5 seconds. Now my T1, most students will often say, well, T1 is just 0. You got to be careful here, because if you take a look at T1, it's actually 2.0 seconds, and it works out quite conveniently in this case, but 2.0 seconds it is. If I do a quick calculation, I get approximately 12.8, or let's just say 13. Now let's take a look at the units again. If you take a look at the numerator side, you have meters, and on the denominator side, just seconds. So naturally, 13 meters per second. Once again, if you take a look at the magnitude of the slope, it is positive 13 meters per second. Now, since it's positive, what do we label as positive on the graph? Well, you can see that on the graph, I've labeled north to be the positive direction, and since I've done that, what I'll do is I'll call this slope to be 13 meters per second north as well. Okay? And there you have it. That's how you find the slope, or that's how you find the instantaneous, in this case, velocity on a curved position time graph.